Thank you. Imagine your friends are coming over for dinner and you have a very cute little robot that uses HTN, Hierarchical Task Network planning. Here he is. So you're asking it, please provide us dinner. This is its initial abstract task. There's some things you will need to take into consideration, like what's your kitchen equipment like? Do you have friends with allergies? What's the budget or the things that are in the fridge? Now these are facts in its world state. The task network contains rules about how to break down this task into smaller, more manageable subtasks and conditions under which it may do so. It contains information about preferences and priorities. If the first step of breaking it down would be to go to the supermarket and do grocery shopping, come back home, cook and serve, you might want it to have to take the bus if it's raining. And then it contains information about pre and post conditions, like you need a bus ticket before you take the bus, and then after you've taken the bus, you'll be at the bus stop near the supermarket. It's planned then. This is the output of the planning process, and it's an ordered to-do list of tasks. It can be partially ordered, meaning that it doesn't matter in which order you get your groceries, as long as you then pay for it before leaving the store. So, hi everyone, my name is Tim Verweij. I'm a principal AI programmer at Guerrilla, and I've been a member of the AI team for 18 years, during which I worked on 5 of our titles, both on AI systems and AI behaviors. And I've worked on HTN technology for about 10 years. Well, I really want to talk to you about HTN, but more specifically, I'd like to talk to you about how we generate backtracking code. So that will be the focus of my presentation. Before I do so, I'd like to tell you about 3 of my colleagues who are key contributors for our HTN technology. Robert Marcus researched planner technology, which led to us using HTN, and he implemented the first planner in use at Guerilla. Hielke Kleve created a tool that is called HTN Translator. It transpiles our HTN descriptions to C++, and this is still the approach that we build upon today, and it's the focus of my presentation. And then lastly, Ricardo Desmet made a Visual Studio Code extension for our HTN description language, which makes our life a whole lot easier coding behaviors, but I won't be talking about that today. So we've been using HTN since Killzone 2, which predates the name of our engine Decima. More recently, though, we've used it for Horizon Forbidden West, and it's also been used outside of our studio by Kojima Productions for their game Death Stranding. So for those not familiar with those games, let's have a short look at those. I brought a trailer which was made for our 20th anniversary last year.
It's been a long journey getting here, but today, on behalf of everyone at Guerrilla Games, I am delighted to finally unveil our newest franchise.
For some historical context, I'd like to take you back to 2005. Guerrilla was looking for a new AI engine. Gilson 1 had used fixed, static plans and calculated a score to see which one had to be executed. Because they were static, it was hard to make exceptions for specific situations, and there was no systemic way to convey information from the utility function to the actions being executed. Furthermore, the code was considered inelegant, containing lots of nested for loops like these, going over all of the possible enemies and weapons, for example, to see if a certain condition applied. Now, wouldn't it be nice to have the flexibility of dynamic plans and solve those other issues at the same time? Well, we found inspiration in a planner called JShop2. This is an HTN planner developed at the University of Maryland. And by taking its approach, we could have dynamic plans. The planner could convey the information required to the plan being constructed. And because it used an implicit search algorithm in its query language, we could, like in Prolog, it was in a way declarative. We could write something like this. We could write something like this instead of our for loops. And the planner would just take care of finding all possible combinations. Now, before I start explaining how this works, there are two comparisons I'd like to make. One is to behavior trees. So behavior trees reason about what is now. There are many things I could say here, but I'll keep things general. So behavior trees reason about now, while planner approaches could reason about future state. There's a strong separation in planners between selecting the actions and then executing them later. And behavior trees often have a blackboard that is a key value store for their knowledge representation, while our AI world state can contain facts that are named tuples of any size, using a variant type that can contain symbols, numbers, lists, object pointers, etc. And with it, we're able to capture the relations between objects as well. And then we have a very powerful query language to query that state. I'll be telling more about it shortly. So the other comparison is to HTNs in games. So Transformers Fall of Cybertron used an HTN. There's an article about it in AI Game Pro, the first book, and it's also available online. And then released just yesterday is Metro Awakening, which is a VR game that used this specific plugin for Unreal. Now, there's something that these two planners do that we don't, which is that we do not model the changes in the world state during planning. So, meaning we don't take into account the consequences of the tasks during planning. That seems like a deal breaker, but we don't reflect that in the world state, but instead we can capture a future state in our local variables and then pass that along as parameters in our task network. And since these two planners use the Unreal blackboard, they also have the same key value knowledge representation. So what kind of queries can we do? What are these powerful queries like? For that, let's go back to our beginning example from the beginning. So your robot knows about what's in the fridge. In Decima's HTN, that might look something like this. So we can query this information then. You have milk in the fridge. Well, there's no matching fact in the world state, so this query will result in failure. You could ask, do you have any item in the fridge? And here, item is a variable, as you can see by the question mark at the front. See this as stating a problem and then asking for which value of item is this query true. So then it will find the matching, one matching fact, a cheese. And from this point, while your query is still active, you can keep asking what else? What else applies to this condition? What other values can you find for item? And then it will find the other ones, and you keep asking what else. And then this is in essence backtracking. So finding an alternative solution to a query that was already evaluated successfully. Eventually though, you'll run out of answers. And if you then keep asking for more, the solver will return failure. Let's now look at a visual representation of this. So those of you that know Prolog may be familiar with this. It's based on a bird box model or a procedure box model. And see this as a solver for a specific query. You could take this query in mind, but the process applies to all conditions. So we'll try to find a solution for our query. These circles represent entry and exit points. They're called ports. So we'll start off at the top left, invoke our problem solver, finding a solution to our query. And then this also creates a choice point when applicable. Now a choice point is a point in our flow to which we can come back and then find an alternative flow forward. So this is our backtracking point in essence. It also carries with it a bit of state to remember where you left off. This also binds our variable, as we say. So the item variable will get its value here. But then if you don't find anything in your fridge, or you don't find any applicable answer to your query, we'll go out the fail port. If you do, we'll go out success. And from this point, we can start asking what else. We can start backtracking by going through our retry port. This will then unbind our variables and reconsider their value. And as long as you have alternative answers, you can keep going in this loop until you run out, and then we'll move to fail. Now let's have a look at how we can do compound queries. For that, let's add another fact to our world state. So your robot also knows about your friend's allergies. Now let's have a look at how we can combine two fact queries. So now we'll find an item in the fridge for which we know there isn't a person allergic to that specific item. See this as finding the item and the person for which this whole thing is true. But there's another way to look at this, which is first find the item. And here item is an output of the first query. We say that it binds the variable item. And then the second part of the query binds person and has item as an input. Of course, we'll find the only matching pair. But let's now look at what that looks like visually, because we can start nesting these boxes like this. First finding the item, and then, if successful, we find the person, the matching person. Now, let's say we find cheese first, and no one is allergic to cheese. Then we'll go back from our failure of the second subcondition back to subcondition A, finding another item, and then going back to B and finding eventually our matching pair of of values. Now, from here we can ask him keep asking what else, but because there aren't any other pairs of matching variables, we'll eventually move out failure. Let's now look at one more Boolean, I should say, logical operator. Negation. So we can negate the second part of our query, now asking for an item for which we know there is no person allergic to this item. And of course, it will find those other items. But I want to highlight one specific property of this second part. So we only need to find one person for which we know that it has this allergy. We don't need to find another as soon as we do, because then we know not having that person is false. So what does that look like visually? Now, in order to hook this up, this is the first time where we're talking about not wanting to find all possible alternatives. We want to skip some of the alternatives. So we'll model that explicitly in our flow here by adding more ports to our box model. We'll have a cut port on the right, which is hooked up to a break port on the left. And they're always hooked up right like this. And it skips the choice point. Now we have to go back, before I show you what the not box looks like, we have to go back to our AND box, because these also have these ports. And they're hooked up like this, because we evaluate subcondition A first and then B, and going then the other way, we need to skip B before A. So let's look at the not box then. So we're trying to prove that there is no such person that has this allergy. If we indeed cannot find any allergic to fact, we can transition from failure of a subcondition to the success of the outer condition. If we do find a matching person though, we don't need to find another person, so we can skip the alternatives of our subcondition. So what we do is bind the success port of our subcondition to the cut port of our subcondition. Then we move out the other way and then move to failure. And because there are no two ways of not having something, we can hook up the outer retry directly to failure and the outer cut directly to break. Now, by now, I'm sure you're thinking, well, how does this apply to your games? How does this work in your games? So I'd like to leave these boxes for now and show you an example of a machine in Horizon Forbidden West's DLC, the Burning Shores. This is the Sting Spawn. It's an insect-like machine that flies in swarms of up to 4. And like all autonomous AI in our games, it uses HTN. So let's have a look at that. So 5 times a second we'll ask it to behave. This is its initial task. The things that it has in its world state are things like its position of enemies, information about its group role, attacks, and weapons. And then the plan consists of things like move over there, trigger an animation, or an attack, or send a message to another agent, or face a certain direction. Let's have a look more closely at a specific example of the Sting Spawn. Here we see it picking up a resource, a metal resource, that will bring to a nearby machine for processing. Now there are 2 facts in its world state that are involved in triggering this behavior. Let's have a look in our in-game debug view for the world state. Here I've filtered out the ones that apply to this specific behavior, and these are facts that come from our group system. Now I won't be going into detail on our group system, but suffice to say it writes these facts to the world state. It knows that it is a resource collector and it should be picking up this specific resource. So how do we go from our initial task behave to a full plan that executes that behavior that we just saw? Well, let's have a look at what our code looks like. We write methods. So these methods detail how to break up one task into a sequence of more specific or smaller tasks. In some cases, it can be just one task. Now we have alternative ways of breaking that down. So we have branches. If you have an enemy, this says, then you should try planning to do combat for that specific enemy. Now, if you don't have any enemies, you do idle behavior instead. Here, combat is of higher priority than idle behavior, meaning it can interrupt idle behavior as well. Let's now have a look then at do idle behavior. So here we have the matching method for that task, and it too has 2 branches. will either grab a resource, this is the behavior we just saw, or will follow the swarm leader. And this can then happen under these specific conditions. On the top branch, we see our facts that we saw before, our role, which is a resource collector, and we can get the resource from the world state as well, and then pass it along to this method. Now, if a method fails to decompose, as we say, if it fails to break down into smaller tasks, we can go backtrack here, and we can try the other branch instead, so still follow the leader. Let's go on one more step to our move to grab resource. So here we see we got a resource as a parameter, and after checking that we've not already grabbed this resource, we can start our plan, which is in two parts, moving there and then grabbing the resource. Now I want to skip ahead and show you what the plan looks like in our plan debug view. So here you see our plan. You see the name of the plan and its arguments, and we can see the tasks that were the result of planning these two parts of our plan. The first task here being the result of planning the movement to this location, and then all of the other ones are the result of planning grabbing the resource. Now, I won't be able to go into detail explaining each of these tasks, unfortunately, because what I want to focus on now is the HTN translator. How do we translate these queries to C++? So the translator was made as an optimization. The C++ is compiled to a DLL, which we then invoke from our main game executable. And each method is translated to one function. And in the generated code, we don't do any we don't do any heap allocations, I should say. Everything, all temporary state is on the stack. And we try to follow the flow of those box models as closely as possible. So what can we do? What do we do in our code to achieve that? Well, there is a statement that has a bit of a bad reputation, but it's very applicable here. So we use goto. We use it a lot. I wouldn't use it in handwritten code. Maybe there are some uses for it, but I'll try to avoid it. But it's an indispensable tool for creating this backtracking code. Well, fortunately, I've never seen a dinosaur in our office that was out to get me, so I think we're fine. Unless, of course, you count these guys. So let's now follow the steps of the translator and see if we could translate a query ourselves. This query. This is a query that the swarm leader can do to find a follower in its swarm. Here the swarm group is an input, and the follower variable is an output. Now you see the same box here as we saw before, but instead of going from left to right, we're going top to bottom, and we'll be filling this with code instead of more boxes or shapes. Now see this code as being a for loop shattered into its components, into its pieces. So we'll iterate over world state facts. Our iterator is on the stack, and then we get our iterator to the first fact. Now, if we don't have any of such facts, we can skip to our failure label. Now, the failure label was already given, and the break label as well, because the translator knows in which context it's translating this query. So we can jump there by using goto. Now, if we do have such a fact, then we can prepare our query, setting any dynamic variables in our query, like the group, and then perform the matching. If it doesn't match, we'll just check the next fact instead. So this closes our for loop. But then if we do find one matching fact, we have our output, of the fact, and we can set that as the value of our follower variable. And now we've already reached the end, the bottom, and this is all there is to it to create this is all the code that needs to be emitted. But there are two more things that we need to do. We need to set our retry label, because if you want to go backtracking, you want to go here. And our other label, cut, does not need to do anything than just not jump there, and then we can just jump over this bit of code. And with that, our example is complete. Now, let me then show you how, let me show you one more box example. I want to go back to showing you one box example, and for that I need to introduce a new type of query. So the sting spawn leader can interact with its followers, but it will only try to interact with nearby followers, skipping the ones that are lagging behind. There's a bit, the task, the matching method of this task could look something like this. I'm leaving out a lot of detail here. That's because I want to focus on this query. So this hash symbol means the condition is defined somewhere else. It means it's a condition in a function, basically. It's what we call an Axiom query. And its definition looks like this. So here we find our follower that is at a certain distance, which is no more than 3 meters away. So it's this what I want to show you, how this query is hooked up to this definition then here. And for that I want to introduce 3 views, 2 function views and 1 of those box models. And I want to show you how everything is hooked up, and I'll introduce each view in the beginning. So the first view is that of the Axiom function that has a generated code for this specific condition. On entry of this function, we'll evaluate this condition, and we'll come back to this later, because the second view, so this corresponds to our Axiom definition. The second view is that of the method that contains the query. So when entering this, this function will evaluate the first branch and its first condition, and then somewhere there is our query. And the third view is that of our zoomed in box of this query. So we'll zoom in here. Now what can we do here to hook up to the Axiom condition that's in the other function? Could we just call into that function and then just return success or failure? Well, that could work just for one specific value, but what do we do if we want to go backtracking? Because the state of that function has been lost, we've returned, and the backtracking state was on the stack. So let's start over. So we want to call into this function. We don't want to return, but we still want to end up here. So how do we do that? Well, we call into this function, our method function, a second time, and then jump here, skip all the bits that we have already evaluated, and jump to a label that we define here, our success label. So from a call stack point of view, you'll have your method function calling into your Axiom function, calling into your method function again, and then jump here. Let's make that a possibility. So we zoom out, and now we create an alternative flow from the start, from our entry point, checking an entry label variable, and if that's set, we'll jump to the corresponding label. Now that we've done these preparations, we can zoom in back to our Axiom query, where we set this variable, this entry variable, before calling into the Axiom function. So let's now follow that function call. We're in our Axiom function now, and from there we'll evaluate the condition. Now on success, we'll call forward to that method that we came from. So we'll have our method Axiom calling into the method the second time. Following that call then, now we're here, but we made our preparation. So we've set our entry label variable. So we can jump here. And then back in our Axiom query box, we have arrived at our label, but keeping the state of the Axiom on the stack. And then if we want to do backtracking, we can. And if we want to skip our choice point, we can. We return that as a value. So we return back to our Axiom query that we want to do backtracking or we want to go to our cut port. There's one detail here, which is that we want to set our re-entry label to ensure that we can end up back at our success label again. And so we return to our Axiom function. And returning from the second invocation of our method back to our Axiom function, we'll check our return result. Do you want to do backtracking or do you want to skip backtracking and move through the corresponding port? And with that, we've closed the loop for backtracking, but then eventually we'll run out of alternatives, or maybe we skipped the backtracking and we went out the other port. So if we go out the other side, we'll return from which port we have, through which port we have exited our subcondition. And then coming back from our Axiom to the first invocation of our method, we'll check the return result here and move through the corresponding port of our Axiom query box. And with that, all of the ports have been hooked up and the Axiom query box is complete. So how do we start debugging something that looks like this? Well, truth is that we don't. At least not directly. So we don't debug the generated code. What we do instead is that we record the decomposition process. So here's our box, and we'll add logging code to these key positions. And we'll also log all of the variable bindings. Now with this information and also logging each entry of a method and an axiom and each branch, we can construct a tree that represents the entire decomposition process. And with that, we're able to show in our in-game debug view not only why a certain plan was selected, but also why a higher priority plan failed to decompose. So I want to show you what that looks like in our in-game debug view for the decomposition. Let's go to the sting spawn for one more example. So the leader role switches every now and then to create an interesting swarming, chaotic movement, like this. And the leader of the swarm will only do this if it knows that all of its followers are nearby. Now this condition is also in an axiom like before. And its implementation is very similar to the query that we saw before. It's coded as the double inverse. So there's not one follower which is at a distance which is greater than the supplied max distance. It looks like this. So we can query this like before using this syntax. And let's now look at what that looks like in our in-game debug view. So I've paused the game here. At the moment, the leader role switches. And we can see our axiom right here, our axiom query. We can see it evaluated successfully because failed conditions have this red cross as one of the conditions higher up. And we can open up the axiom by clicking on it. And then we can see for example, its arguments. We can hover over them to see their values. And then we can see here that the other member effect was actually backtracked over, meaning that there were multiple alternative solutions for the follower. Now we can select our first follower and then see what happened next in that specific flow. And here we can see that it failed at the check greater than, meaning that its distance was actually less than or equal to the supplied distance. And this is what caused it to do backtracking, going back to the other member. And then we can follow the backtracking by opening the second one. Or the third one, and we can see that indeed all of the members were closer than the supplied maximum distance. And with that, we can close up our Axiom. And this concludes my demo of our in-game debug view. Now, this also concludes my presentation, in which I've given you some a small look behind the scenes of how we use HTN and how we generate code that does backtracking. And I hope I've inspired you on the topic of visualizing control flow or generating code. Maybe you'd like to have a look at HTN yourself. And if I'm not mistaken, I think dinner is served.